Hello everyone, today we're going to be doing practice homework 4 in Stata. So first things first, let's go find this data file on Blackboard. It's pizza.dta. We have 35 individuals and their annual expenditure on pizzas. That'll be our dependent variable. We have their individual income in thousands of dollars and their age. And we're going to estimate the following model. Pizza equals B1, beta 1 plus beta 2 age plus beta 3 income plus beta 4 age times income plus our error term. So first things first, let's go to Stata, open up this data file, take a quick look here. We got a bunch of variables here. What we're interested in is income, age, and pizza. Remember, this income is in thousands of dollars. So the first thing they ask us is to estimate the model above and give a publishable and precise interpretation of the results. So we have age, income, and the interaction of age and income as our explanatory variables. So the first thing we'll do is create this variable right here, age times income. So number one, generate age income. Let's say income age flows better. So now we have that interaction variable, and we can regress pizza, age, and income, and then income age. So when we run our regression here, we get four different coefficients. One of them's our constant. None of them seem to be significant at the 0.05 significance level. We want to give a publishable and precise interpretation of the results. So we want to make sure we mention that none of these are significant on their own, but we could say that as age increases, we estimate that pizza expenditure will decrease. As income increases, we estimate pizza and expenditure will decrease. And then for income age, this is negative, so we would say that either the marginal propensity to consume with respect to age decreases as income increases, or that the marginal propensity to consume with respect to income decreases as age increases. But again, our p-values here are not low enough to really publish these results. So we want to make sure we mention that in our interpretation. Let's move on to number 2. Now we want to test the hypothesis that age does not affect pizza expenditure. Since we have two variables with age in them, this is going to be a joint hypothesis test. So we're testing the hypothesis that B2 and B4 is equal to 0. So for this, we're going to need an F test. So if we look back at our notes, we can see that the F statistic relies on a restricted and an unrestricted model. So the unrestricted model is the one we just regressed, and then the restricted model is going to be the model that we get if we assume our null hypothesis to be true. This J here is going to be the number of restrictions, N the number of observations, and K the number of coefficients in the unrestricted model. So if we plug all these numbers in, we'll get our F statistic. So first, let's start with our restricted model. So up here we have our unrestricted model. If we have B2 and B4 equals to 0, then we get the model pizza and income. So here's our restricted model, and we want to use this sum of squared residuals from our restricted model, and this sum of squared residuals from our unrestricted model, and just plug those into the equation for the F-stat. So display F-stat. Sum of squared restricted minus sum of squared unrestricted divided by the number of restrictions, which is 2 here. It's the number of equal signs in our hypothesis. And then all that over the sum of squared restricted divided by n minus k, where n is our sample size and k is our coefficients in our unrestricted model. So if we run this, we get fstat equals 4.7237. So we want to compare that to an f critical value. So we can say display f critical value, and this is going to be, you can get this from the inverse f tail function, and we have the first degrees of freedom is 2, the second degrees of freedom is 35 minus 4, and we'll say a 5% significance, and we get 3.304. So since our f-stat is greater than that, it lies in the rejection region, and we would reject the null hypothesis that both of those are equal to 0. So we can't say that, again, referring back to these p-values, none of our coefficients are significant on their own, but we know that the joint hypothesis, that age has some impact on pizza expenditure. We can reject the joint hypothesis that it does not have any impact on pizza expenditure. And then we can find our p-value here if we wish. We can say display p-value and this is just going to be the same, and then we'll put our f-stat here. So we want to see what the area to the right of this on the f-tail is, and we get 0.016. So that's our p-value. It's less than 0.05, so we can reject it at the 0.05 significance level. Alright, so we have part 2 to number 2. Construct point estimates and 95% estimates of the marginal propensity to spend on pizza for individuals of age 25, 35, 45, and 55. Comment on these estimates. So, what is the marginal propensity to consume? So that's the change in pizza expenditure given a change in income. And we want this for ages 25, 35, 45, and 55. So if we do that in terms of our model, if we take the derivative of both sides with respect to income, then we'll get this marginal propensity to consume is B3 plus B4 times age. So our marginal propensity to consume, or the partial derivative of pizza expenditure with respect to income, is dependent on age. So here we just want to calculate this for these 4 different ages to kind of get an idea of what that looks like. So the first thing, we'll get our model back in our memory, our unrestricted model. Oops. So now we have our unrestricted model back in our memory. We can say local marginal propensity to consume is equal to B3 plus B4 times 25. And then we'll just make sure we display that. So when we run this, we get the marginal propensity to consume for a 25-year-old is 3.377. So we estimate that if a 25-year-old sees a $1,000 increase in their income, then they will increase their pizza expenditure by $3.37 on average. And then we need to, since it asked us to find a confidence interval, we should find the standard error of the marginal propensity to consume. Since the marginal propensity to consume here is a linear combination, we have to make sure we find the variance and the standard error the right way. So we would say variance of B3 plus B4 times age, this is the variance of marginal propensity to consume, is equal to variance of B3 plus age squared. When you take it out of the variance, it becomes squared. Variance of B4 plus 2 times age times covariance of B3 and B4. So we can get these variance values by saying E stat VCE, and we want to look at the variance between income in itself, that's B3, the variance between income age in itself, that's B4, variance of B4, and then the covariance between the two, so income and income age. So that's what we're going to plug into our formula here. So we can say local standard error was square root, and then we put in the variance of B3 plus B4 times age in here. So I want to say variance of B3 plus age squared times variance of B4 plus 2 times age, here's 25, times covariance of B3 and B4. And then we want to display that. Remember, we have to use these weird little quotations when we're referring to local variables in Stata. And we get a standard error of 1.422. So now we can use that to make our confidence interval. %, confidence interval for 25-year-olds. That first bracket, and it's going to be marginal propensity to consume that we estimated minus standard error times NVT tail. Get the degrees of freedom from the regression, and then 0.025 on each side will give us a 95% confidence interval, and then the upper bound is just that with a plus. So don't forget here that you have to run it all as one big block, because your local variables will not be stored in memory otherwise. So now we can get our confidence interval for a 25-year-old. And then to do this for the rest of the ages, 35-year-old, 45-year-old, 55, we can just copy and paste this and change the age, so everything else will be the same. And then if we run it as one big block, we should get a confidence interval for a 35-year-old. Remember, this is saying that their marginal propensity to consume is somewhere in this range. We're 95% confident that their marginal propensity to consume falls in this interval. And then just repeat the process for 45. Should get a new interval here. And so these are overlapping, so that kind of signifies that they're not significantly different for these different age groups. And then put some space in here. Always good to stay organized. And then 55-year-old. And there we go. So later on we'll get a similar question and we'll show a shortcut way, but it's important to understand this so that you know the process that's going on and how we're finding the standard error for the marginal propensity to consume, and then using that to create the confidence intervals. But there are shortcuts in Stata. So number 3 asks us to modify the equation to permit a life cycle effect in which the marginal effect of income on pizza expenditure increases with age up to a point and then falls. Do so by adding the term age squared times income to the model. What sign do you anticipate on this term? Estimate the model and test the significance of the variable. Did the estimate have the expected sign? So age squared times income, that's what we're adding because we're trying to model a life cycle effect, where the marginal effect of income increases with age and then falls. So if we take the partial derivative with respect to income of this term, then we get age squared. So this is telling us how the marginal effect of income changes with age. So if it's increasing up with age up to a point and then falls, that means we have an upside down parabola. So this term we expect to be negative. So let's estimate this and see if this term is significant and if it is negative, which is what we expect. So we have number 3. First thing we need to do is create that variable. So income age squared, and just say income times age again. And then we can estimate our model. Pizza expenditure is our dependent variable. Then we have age income, and income age, and income age squared. So when we estimate our model, we look at our coefficient on income age squared. It's small and positive, so it's not what we expect, and that might have to do with this really large p-value. So we would not say that this is significant. We did not find the effect in our data that we were looking for. This could be because of the small sample size, but for now we see that it's not very likely that this effect is present in our data. So then, using model in part 3, construct point estimates and 95% estimates of the marginal propensity to spend on pizza for individuals of age 25, 35, 45, and 55. Comment on these estimates in light of the values in the range of the sample data. What can you say about the quadratic function of age that describes the marginal propensity to spend on pizza? So for number 4, we're going to use the shortcut in Stata to find these confidence intervals and for the different ages. So what we have to do is we have to use the regress model differently here. we have to formulate it differently. So it's going to be the same regression, but it's slightly different notation. So when we put our interaction variables in here, instead of coding them as a separate variable, we have to put both of the variables we're interested in. The c.age tells us that age is continuous, and it's interacting with c.income. And then we have c.age with c.age with c.income. So this is going to be the same regression as we just ran in number 3, but because we formulated it differently, we can now use the margins command. So Stata can do automatic testing and confidence intervals with this form of the regression. So we'd say margins dy dx of income at age so we say 25 is the lowest. We want to go by tens all the way up to 55. Need this dy dx income should be separate, and then at looks like it works. And now we get 95% confidence intervals based on this new model, which has the age squared income term, and we have, so this would tell us for a 25-year-old, this would tell us for a 35-year-old, this would tell us for a 45-year-old, this would tell us for a 55-year-old. And here there's not a real clear pattern to these. They're overlapping, so we wouldn't say that they're very significant here. Our model is not very predictive of the marginal propensity to consume. For part 5, it asks whether all 3 coefficients, age times income, and age squared times income, significantly differ from 0 at the 1% significance level. So we're going to carry out a joint test for this. This is the same thing we did as number 2, except now we have another coefficient, and we're going to use the shortcut method to accomplish this. So we'd say test age. Remember, this is referring to our regression, so make sure you have the correct regression. It was the last one you ran. That's the one that will be stored in memory. And we want to put each of the terms that we want to test. So we have the coefficient with respect to age, the coefficient on the interaction of age and income, and the interaction of income, age, and age. So when we test this, we get F statistic of 3.24 and a probability of, so this is our p-value of 0.0358, and since this is greater than 0.01, we would say that we do not reject at the 1% significance level. So these estimates are not significantly different than 0 at the 1% significance level. So we'll probably need a better model if we want to move forward with publishing these results in a real-world scenario. Okay, that's it for today. As always, let me know if you have any questions. Make sure you code along with this so you have all the experience doing these both by hand and with the shortcut methods, so it's a lot easier for you when you attempt your homework. That's it.